Hey, good afternoon, everyone. My name is Tom Douglas. I'm with Rayco. Thanks for joining us today on our webinar about critical HVAC systems. Leading our webinar today is Bob Bove out of TSI, their National Accounts Manager, and he's got about 20 years experience in all kinds of different HVAC and industrial hygiene instrumentation, so he's got a pretty solid background. So we thank him for his time and his knowledge. A couple of housekeeping items. First of all, we will be recording this webinar, so if you miss a part of it or you'd like to watch it again or send it off to a friend, that will be available to you. Same with the slides. We'll make the slide deck also available, so if there's something you wanted to see or spend a little more time taking a peek at, that'll be available to you. And as we go, if you have any questions, everyone should have a question tab kind of on the upper right-hand side of your screen. We'll make sure we get to all questions towards the end of the presentation, but if anything pops up, be sure to type it in there and we will address it. So that's about it. Bob, I'm going to pass it over to you. Thanks so much, and here we go.
Oh, you're welcome. Thank you so much, Tom. Good afternoon, everybody. This will be fun. It really is built and put together as a sort of an introductory webinar to explore critical HVAC. It's a very deep topic, and we just don't have the time or the equipment here to go really deep into it. But I want to give everybody attending today a little bit a little better idea of what I term critical HVAC, what it's all about. We're going to go over some of the unique requirements. What makes critical HVAC different from just regular every old day HVAC systems and operations? There are unique requirements, standards, regulations, and performance that are needed to actually be operating in a critical HVAC condition, and some of the different instrumentation that's required. It's not your typical old $1.99 rotating vane that's going to do the job in critical HVAC. So let's get into it. Some of the things we want to cover today and make sure we get a good idea about is making sure you know some of the common problems that are there in critical HVAC. Talk about some of the instrumentation, the way they're designed, why they're designed the way they are. Understand the difference in the paperwork that goes along with instrumentation and with critical HVAC instrumentation and the job. Specifically the difference between certificates of conformance and actual calibration or a NIST certificate. I know from experience a lot of people are confused about that. They think they've got one, they've got the other, and when it comes time to get audited, then they're in trouble. And basically to quickly discuss trying to save time, trying to save money, using the right instruments, using the right techniques. Everybody loves a top 10 list, so I put together basically a top 10 reason, a listing of why HVAC systems don't perform as intended. And again, the difference between the AC unit sitting in your window, cooling your house, and the 50-ton sled up on top of the roof cooling an office building, the only difference between the two of them is size. They both do exactly the same thing. And they both rely on the same infrastructure and installation to perform the job. Number one, ductwork. You can't have an HVAC system without some type of ductwork. And number one, ductwork we find normally is not reinforced to cover the SMAC and the pressure classifications. Jobs are bid very, very tightly. Materials are constrained. They just don't do the job properly. Second most important reason I find often is ducts are just not properly sealed. Again, time constraints, working through, trying to get the job done on time, trying to work with limited resources. Even on critical applications, I find ducts very, very improperly sealed more than half the time. Also find that return and exhaust ducts are not sealed properly as well. So you're losing a lot of the dynamic performance of the system by not doing that. Number four, again, time constraints. People look at a commercial application and sometimes they just fail to adequately pressure test the ductwork. I think there was a recent study done at the middle of last year. I'll have to think. I'll have to find the reference for it. But it was found that roughly 50+% of HVAC systems, commercial HVAC systems, have more than a 30% by volume leak within the system. So that's just money down the drain. Number 5, just not understanding duct construction standards as specified by SMACNA in the fabrication and installation. That's just not right. And just as important, we talked about sealing, failure to seal the return ducts. I mean, this proves duct sealing is effective if you do pressure test the system. In residential applications, I mean, the easy way to determine is duct loss is to have the HVAC system off and all your exhaust fans on. It's a little more complicated in commercial applications, so duct sealing is quite important. Number 6, failure to properly install the turning vanes. I mean, that's fairly common. Number 7, we're talking about mostly in critical HVAC commercial applications, and these are higher velocity systems, many times approaching 2,500 CFM. And these high duct velocities, not only do they create noise, they increase the pressure drop in fittings and ductwork. So that's another hurdle that has to be overcome in a critical HVAC system. Not understanding the fan system effect can also compromise fan capacity. And again, that goes right back to the system design, right on up through the operation phase. A lot of times, drawings don't have the proper dimensional sizes. And in commercial applications, it is very important to make sure that you're faithful to and following the schedule and the installation drawings. Even when going back and doing routine maintenance. I mean, a common situation is misinterpretation, usually resulting in improperly sized ductwork, either under-designed or over-designed. I know the old saw is over-design the system. That's guaranteeing you're wasting money. But not knowing how to install retrofit in RX or CX in retro commissioning systems by not having adequate documentation is as big a problem. And number 10, we do see this fairly often too in the many critical HVAC systems, just not having enough room for roughly 4 duct diameters prior to upstream of a VAV box. I mean, if you want turbulence, crawl through any duct system and observe for yourself. It's very important to try and get some laminar flow into a VAV box so that you've got control operation possibility. So that runs in fairly often. So that's my top 10 list. I wanted to come up with 3 typical problems in critical HVAC that you see most often. One of them is the velocity near the sensor is too low, and lower airspeeds near sensor detection limits are a common problem in critical HVAC systems. Why is that? Running an HVAC system costs money. One of the goals to save money. A lot of people mistakenly think ratcheting down the volume helps save energy. It doesn't. It's almost as bad as going in your home, going through your system and closing vents, thinking you're going to be saving money and reducing money expenditures on your HVAC system. What you're doing is probably over the long term inducing a pretty good calibrated leak into your system, especially if you've got an HVAC plant in the basement or up in the attic that's a constant volume. It doesn't know you've turned the vents off. So reducing fan speed below the system curve, as you see there, just doesn't do your critical system any favors at all. We often see uneven air velocities and plenty of turbulence. I mentioned turbulence before. That diagram kind of points it out. if you take a cross-section of a duct, you can see the air profiles between the outside air intake louver and the outside air damper are typically very non-uniform. There's large eddies. You can see turbulence and non-uniform velocities really can develop between the louver and damper, making accurate static pressure measurements pretty difficult. Might be a reason why a lot of HVAC techs kind of hold off doing static pressure measurements on systems because they know they're going to run into this. Even in critical HVAC systems, outside air flow rate measurements really are most critical when the dampers are mostly closed and the minimum amount of air is being supplied to the building. So again, in the outliers of environmental control, you got to make sure that your settings are proper. A lot of engineering systems take a look in the duct. You might or might not see flow straightening devices used, but there only needs to be a consistent relationship between the outside airflow rate and the output signal of the HVAC sensor system to be working properly. So that needs addressing. The third typical problem in critical HVAC, I see it all the time, is backwards airflow through the outside air damper. And you would think, how can that be? That's an innie, not an outie. Well, there's turbulence there. In many designs and many installations, turbulence causes pressure differences and also contributes to reversed airflow. I would say, as a rule of thumb, I hate to do this, but it's worth bringing up. In general, when the pressure drop across pretty much all the portions of the damper is greater than 0, that may be enough to prevent reverse airflow. Let's say a pressure drop across the damper greater than 0.04 inches of water, or about 10 pascals, should be enough to prevent reverse flow. Checking that is certainly a worthy measurement to be made. We're talking critical HVAC, and if you're in that business, you're in that part of the operations. I like to say you're not in the business of estimation. Guessing doesn't get you anywhere. You're working on a critical process, and the critical processes do require critical measurements. For example, on the HVAC maintenance measurements, it's been lab proven time and time again, have potential to save significant amount of energy. Any of the used measures have a significant potential for energy saving, both in residential and commercial HVAC systems. The first one being primarily airflow adjustment. So getting the first measurement in HVAC and critical HVAC airflow right pays big dividends. Because of this, the success is really, I think, in the hands of the technician in the field. And the likelihood of high quality work is affected by several factors, not only following and accept procedures, I think, but whether the technician has actually calibrated his or her instrument, and not just having a primary backup instrument. What's the old saying Confucius say, man who wears one watch always knows what time it is, but man who wears two is never quite sure. I always end up talking to a lot of technicians who have a backup instrument in the truck. Why? If your primary instrument is calibrated, is working properly, you need to rely on that and not confuse yourself with a lot of additional instrumentation. There's a good paper at the ASHRAE conference back in the June meeting in San Antonio that goes over this much better than I can. That's worth reading. I think it was by Heinmeier. How do we define critical HVAC? I think that in my mind there's three ways to go about the definition. One is by talking about the actual parameters that are measured. Another way might be to talk about the specifications that are required for an HVAC system operation. And the other way is to maybe look at the controls that are thrown on the top of that system. We talk about parameters. I mean, the most common, obviously, we're talking about airflow. And a definition of HVAC, critical, residential, or otherwise, in my mind, is moving expensive air from point A to point B, arguably efficiently, double arguably affordably. So airflow movement is the first. Second parameter they all enjoy is pressure, and the only thing that moves air is pressure. So getting the proper pressure measurements is essential. I think number three, temperature. Temperature is always a measured parameter. It is possible if you're doing balancing work, any of the tab guys out there, I mean, if you're careful, you can balance a room using just temperature and not any other measurement. But it's an essential part right alongside with relative humidity. That's the other side of comfortable, I like to call it. So they both go together. On the critical side, there's a few more. There's another important parameter, dew point, and it's not just important for air conditioning calculations. Many critical environments rely on dew point. Environments such as data centers, semiconductor fabs, powdered pharma production, I guess, and packaging, powder coating processes, and all those. They rely on an accurate dew point measurement, and I stress an accurate dew point measurement because they're relying on that for total control. If you talk about specifications, you know, there are so many written, not guidelines, requirements, laws, strictures by different groups in healthcare, medical device manufacturing, semiconductor, microelectronics, plasma display, that you must follow in order to have a successfully operating HVAC system. So there are higher level specifications you have to rely on. Then third would be control requirements. That's pretty much the difference between, let's say, an ASHRAE guidelines for a typical office versus the requirements for a high-level research laboratory. You're obviously not working both to the same common things as you would. Let's try to define a clean environment. I mean, these are the usual suspects right here, you know, from data processing centers down through healthcare, obviously pharma manufacturing, semiconductor fabs, microelectronic manufacturing, advanced research. Also like to throw in there, some people are starting to now define critical HVAC as some food production. There are there's a growing number of food production processes that are done in clean rooms. There's some outlying applications as well that should be considered. You might consider fine finished furniture being now manufactured and assembled in some type of clean room. If you're spending tons of money for an expensive piece of furniture, you don't want a lot of dust and lint and particulates on the top of your fine finish. They're filtered out in a clean room. The result of not doing these jobs, of not doing these things right, not getting those parameters under control, not operating to the required regulations, you're facing unplanned downtime and possibly catastrophic results. If those two things are completely unacceptable to the application, you're talking about a critical HVAC environment. And I mentioned the cost before, money in operating systems. This slide kind of gives you a quick overview of what it costs to run a typical commercial building. I was very surprised to see these numbers, that roughly half of the money spent is on the HVAC system. That's kind of sobering when you consider all that goes into a typical commercial building. And of course, the bigger the building, the taller it is, the worse that percentage possibly can become. I want to compare that against what normally would be a real critical environment, let's say a laboratory. So U.S. Energy Department has what they call energy use indexes for all the typical operations you see on the x-axis. So from warehousing on through lodging and hospitals, through libraries and retail malls, you can see the relative energy use as it's climbing all the way going to the left up to the top number one, which is a laboratory. And it was, again, surprising to look at 64% of the operating expense for a laboratory has gone to its HVAC, to running the HVAC system. That was as big a surprise to me as anything else I came across. So I wanted to come up with a different idea and say, let's compare what might be termed a critical HVAC system versus a non-critical. And one of the ways I wanted to do it was just let's take three basic parameters. So in the bottom left, you see a chart there. I've plotted on the left y-axis relative humidity, on the x-axis going left to right, increasing temperature. On the y-axis on the right, increasing air changes per hour. If you look at the typical office application over here, you can see it's got offices, it's got conference rooms, it's got the mechanical room, storage, whatever. If I plot those three parameters in, let's say, a typical chart, I can operate somewhere within this box here. It's fairly generous, easy to understand, easy to control, fairly easy to measure using pretty common and pretty easily available instrumentation today. However, if I contrast the needs for these three parameters in, say, a semiconductor fab, I will plot those three same parameters and end up with a control box somewhere around here. These are not exact numbers, but the purpose here is really to show this situation and this situation are completely different as far as relative accuracy, relative precision, and requirement and instrumentation goes. I wouldn't use the same instrument to measure lobby temperature here to measure the proper semiconductor fab temperature over here. They just don't work in those types of applications. So that might be a different way, in my mind, to view critical versus non-critical. Why are laboratories so rough to do? Laboratories really, by design, exhaust 100% of their air. Everything goes out. Nothing is saved. Nothing is recycled, simply because of safety and contamination requirements. So a laboratory, you've got basically two environments: the macro environment, which is the general room, and possibly micro environments, biological safety cabinets, fume hoods, whatever. There's two different environments that need to be controlled. Everything from macro to micro needs to be dumped outside the room, which is a reason why laboratories rarely are, HVAC systems and laboratories and critical areas like these are rarely shut down, because number one, it takes too long to regenerate, power them back up so that they're running efficiency, and number two, it takes too long to reach the target temperature, relative humidity, and air changes per hour for them. What does it mean if a critical HVAC system goes down? This data comes from 2004. I think it's even worse today. But if you look at what would it mean to a retail brokerage, Charles Schwab or someone like that, if their HVAC system goes down and automatically starts shutting down their computers, roughly back then, almost $6.5 million per hour would cost them. And you can go down through the different fees, the different applications here. I was told a while ago by unofficially by an Intel engineer, in any of their fabs, any of their recent more recent fabs, that is a fab that's less than 10 years old, if it goes down because of lack of control, wrong settings, it would cost them roughly a little bit over $1 million a minute in lost revenue. So downtime just can't be accepted in many critical applications, and what people call mission critical as well. Checking, adjusting, preventive maintenance, preventive equipment failure, that means checking everything. And here's why I say critical HVAC is not just getting the airflow temp and RH right. It's required predictive maintenance for the air handling units, the ductwork, the chiller for cooling or dehumidification, checking the towers, making sure that the reject heat from chillers or HVAC units are working properly. You got to look at the pumps, got to look at the engine generator sets. All of this directly affects the proper operation of a critical HVAC system. And it's not just direct measurement. I mean, there are now non-intrusive technologies you can use in predictive maintenance, like vibration analysis, using a spectrum analyzer to record different waveform signatures, infrared thermography to detect potential problems before a failure occurs, and even ultrasonic flow meters for hydronic flow measurement, for VAV boxes if they're there, to make sure that there's enough water, hot or cold, to do the job. Good indication here would be taking an IR gun to take a look and see, is there a problem about to happen? Is my critical HVAC system about ready to be shut down because of a faulty fuse or a hot spot or whatever? So here's a contrast between the thermal image. Here's your hot spot. You can't see it in visible light, but some intrusive techniques are now part of the critical HVAC arsenal of weapons that an HVAC tech would probably be using. I keep saying require a higher level of instrumentation, and that's true. Measurements taken during HVAC maintenance, they're critical to saving energy because they're going to tell you what you need to do, what the remediation steps are that should be taken. So it's essential that you get the measurements right. And for me, there's three basic areas of measurement in critical HVAC. We need to talk about sensitivity. We need to talk about accuracy, and we need to talk about precision. And each one of those has a direct bearing on what's measured and how you measure it. It has a direct effect on the range of the instrument design and its operation. Also impacts the cost of ownership. And that really includes not only the instrument, but any consumables, any service repair for them, and routine calibration. It's going to be different for a lower level residential instrument versus a gotta need, highly important critical HVAC instrumentation. I also hear a lot of people say higher accuracy units are not widely in use. Why? Because of their higher cost, their assumed fragility in the field, and the requirement for periodic calibration. I say specifying and choosing the right instrument not only saves time, saves money, saves retests. Those choices, those direct choices there, are based on the instrument's sensitivity, accuracy, and precision, if you get them done right up front. Let's talk about sensitivity first. I'm sure this guy's thinking about which way on the sensitivity curve do I really want to end up on. If you're looking at your data, you want to evaluate the accuracy and precision of your measurement. It's important to understand, though, your instrument's sensitivity first. A lot of people don't talk about this, but it's there, and it's part of the design criteria, and I think it's important in critical HVAC to understand it. Sensitivity is the smallest change in an input signal that causes the measuring device to respond. In other words, if an input signal changes by a certain amount, by certain sensitivity, then you can see the change in the digital data. So number one, is it sensitive enough to do the job? Second thing, talking high level of instrumentation, I grabbed two charts up from National Instruments. I think oscilloscopes are a really good representation of any instrument talking about sensitivity. They use the term code width, and that's really the discrete level at which the instrument displays values. The resolution defines the code width. So your sine wave there is really where that sensitivity for that instrument lives. Once that sensitivity breaks through the upper lane on the bottom chart, you see it's now within the code width, the measurable code width. That then goes from a flat line digital signal to a step function digital signal as it pops back up above the code width area. So sensitivity defines the change in voltage needed for an instrument to register a change in value. The exact definition of the term sensitivity absolutely changes from company to company. So here's an opportunity for you to dig into and get the definition down and find out what they're talking about. Second term we need to talk about is accuracy. And by accuracy, I mean measure the capability of the instrument to faithfully indicate the value of the measured signal. This term, don't get confused with resolution. Accuracy is not related to resolution. However, just know that the accuracy can never be better than the instrument's resolution. So how accuracy is calculated, that also changes by the device, by the instrument that we're talking about. But you need to always check your instrument specifications to see how particular instruments calculate accuracy. Different companies define and calculate accuracy differently. So it's important that you understand what it is you own, how it performs, and is it right for the job that you're going to do. The third is precision. So we're talking about accuracy before. Let's talk about precision now. Both terms, accuracy and precision, most often are used interchangeably. They shouldn't be. There's a subtle difference. And you take a look at those four graphics down below that, and you can see immediately. You've got all four situations. From on the left, the low accuracy and low precision. They never got even close to the bullseye with the darts. Versus all the way on the right, they're all in the bullseye. That's highly accurate, highly precise. Many critical HVAC applications require both of those measurements, because you're going back to or affecting or going back to the building automation system and telling it, I want more energy to move more air to these locations at this temperature, at this humidity, at this volume, near changes per hour, and I better be right. Also, just know that precision is really affected by the noise and short-term drift on the instrument. And by the short-term drift, I mean both the meter and the sensor that the instrument is using. So accuracy versus precision. Yep, it's up for everybody to define, but it really is important to understand the difference between the two, and to choose your instrument accordingly based upon what you need. Maybe a better way to determine this is here's this poor driver Kobayashi in a race in the middle of a downpour. He's number 13 in the chart. Now, obviously, to this point, on lap number 1 of 14, he's obviously been successful. Number 1, he hasn't crashed. Number 2, he's negotiated the track completely, which means he's accurate. He made all the right moves. He got all through 18 turns properly. The reason he's in position number 13 is he probably wasn't very precise in the way he entered and came out of each one of those 18 turns. So there is a measurable, there is a visual difference between accuracy and precision. Maybe we should define accuracy as the error, is the amount of error as measured from the true value, what the actual true value really is. Precision really is defined, should be defined as any deviation of any one of those individual measurements from their average. And these measurements don't reveal either bias or constant error be present in every one of the measurements. Meaning sensors and instruments, they wear over time, i.e. they drift over time. So that needs to be taken into account. All critical HVAC applications rely on both accuracy and precision. I wanted to show one example that was surprising to me. A study done by Dr. Lee at Purdue University compared an RTD, which is supposed to be much more accurate to a thermocouple. RTDs are more accurate and repeatable than thermocouples and more stable reading over time. Thermocouples have a much broader range than an RTD, respond faster, and they certainly cost less than an RTD. But in choosing a sensor and operating it, you need to know about not only the published accuracy, but the accuracy on the application that you're using it there. And one of the things I found in measuring different refrigerant line temperatures, Dr. Lee found heat transfer to an RTD and thermocouple, the RTD had an error in measurement of about 20% of the total differential temperature, while the thermocouple had an error in measurement of about 1.6%, completely the opposite of what you would expect for that type of sensor. So you need to ask those kinds of questions. What's the accuracy that's needed? What's the precision? What am I trying to control? Did I pick the right sensor and meter for that job, or did I just grab what was on top of the toolbox to do the work? I hear this an awful lot. My instrument comes to the factory is calibrated, and I don't need field calibration. Or the accuracy is prominently documented, but it's isolated, but it may only be isolated to the transducer and not the sensor and electronics. Again, a lot of companies, and again, you need to ask, you need to know what it is you're working with. When you see accuracy, is that the accuracy of the sensor? Is that the accuracy of the measurement unit? Or is that the accuracy of the system, the meter, sensor, and the transducer used to amplify the signal from the sensor? It does have a big effect, and it can be, certainly is cumulative when you're adding up the different inaccuracies. And third, a lot of people forget to ask about, can you please define accuracy for me? Are we talking about accuracy of the reading or accuracy of the full scale? In critical HVAC, it's very important to understand the difference between the two and to know what it is what you're looking at. For example, if you have a 0 to 100 degrees Fahrenheit instrument, full scale with an accuracy of 2%, at a 50-degree reading, that's telling me my temperature could be anywhere between 48 and 52 degrees. I'm not quite sure. It's somewhere in there. But if the accuracy is of reading value for that same 0 to 100 degree instrument, and my accuracy is 2% of reading, at 50 degrees, it's only 49 to 51 degrees error range, and it gets worse the larger the numbers are. I'm sorry, it gets worse the smaller the numbers are. So I try to explain that with this graph here to know the difference between percent of reading or percent of full scale. Never forget to ask which one it is of there. For example, half a degree of full scale gives you an error over here. The lower the percent of meters range, you see how bad it is at the low end and how it all smooths out the higher the closer you get to full scale. Very rarely in HVAC are you measuring over here. Mostly in HVAC you're measuring here, especially in critical HVAC types of flow rates and balancing tasks. So it's really important to understand where you are. Got to also answer, can I work with the instrument? The reason instruments are purposely designed to do what they do because the best critical HVAC instrumentation isn't difficult to operate. They're not difficult to transport. They've got good displays, large displays. Don't overlook the benefit of a backlit display in the instrumentation you're buying. A lot of times you want to see the data in the way you want to present it. Make sure critical HVAC instrumentation is user configurable so that it suits the job and the application. They normally should be employing quality design sensors for maximum output, for maximum performance, maximum benefit. The quality, easy to calibrate, goes right along with quality. Today's best critical HVAC instrumentation, they're both quality and easy to calibrate, benefited by sensors that are smart probes in designs, meaning the calibration certificate travels with the probe. The calibration certificate refers to the probe and the sensor itself and not the meter. Years ago, any offsets or adjustments in the sensor and probe's performance needed to be stored in the meter. Now, today, the best sensors are smart, meaning any offset, any readjustment of performance for that sensor to bring it back into true calibration is stored in the probe itself. it's assuming you're choosing the right sensor, obviously. So you want to be able to balance the accuracy and precision and the ability and the productivity, like we just saw in the last slide, all together. You wouldn't choose an ambient temperature sensor to measure an immersion temperature in water. They're just not designed to do that job properly. And I can't tell you how many times we see people choosing the wrong sensor for a given parameter, even in critical HVAC. They should know better. Many times they don't. I wouldn't take a pitot tube to do the job a hot wire anemometer would do. Hot wire anemometer is great on low flows. If you've got very low flows and I'm looking to measure a low air flow, pitot tube would not be what I grab. Again, a lot of people make that mistake and rely on a pitot tube to do low flows. In handling the data in critical HVAC, we're all tempted to do rounding. Certainly, rounding errors affect the results, and it's not just English versus metric. That I think we all understand. We all know the difference between the two. Most of today's instruments have selectable units, so you can choose what you want, either English or metric. How does the meter interpret the results is one of the most important factors as to what you see on that display. Do they measure in English and convert to metric, or vice versa? It really makes a big difference where they start out from. And a major source of rounding errors, especially in pressure measurements, would be to ask yourself, do I need 2 or do I actually need 3 significant digits for accuracy? Meaning, what's to the right of the decimal point? How many digits are to the right of the decimal point? So many instruments in critical HVAC have 1 significant digit to the right of the decimal point. That just doesn't tell you anything, and it's useless in trying to measure inches of water. It really comes down to, I've got 1 atmosphere of pressure. Is that 696 psi, or is it 14.7 psi? Or do I round it up to 15 psi? I mean, the error is cumulative each time you keep doing that. Rounding multiple times can cause the error to accumulate. So you've got to be careful, again, not only what you're reading, what you're reporting. Currently now, for pharmacies, USP 797 requires differential pressure measurement in compounding pharmacies. So a reading of 0.016 inches of water column, it might be displayed as 0.02 water column. Which one do you report? You've got to look at the requirements for that application. Do they need 3 significant digits, or can they settle with 2? Again, it all depends on what's required for that application. So drift, we all have to live with drift. And there's mechanical, there's electrical, and there's chemical drift. I like to say on this side of the sun, all sensors drift. So eventually something needs to be adjusted. Something you just can't live with an increasing signal as you see here. You need to make some kind of adjustment over time. And that comes down to some more terminology in critical HVAC. It's really important to understand the difference between calibration and adjustment. And I'm just as guilty as everyone else. I use the term calibration quite interchangeably now, and I shouldn't. I really should know better. Calibration is a sensor's acceptable performance as compared to a published accuracy. That's it, pure and simple. Adjustment is making a sensor perform to a published accuracy. So if we accept that and we understand the difference between the two, the adjustment method chosen must meet the sensor design and sensor performance expectation. So when something is, you get back from when you get back from the laboratory and something's been calibrated, you got to take a look and see what the certificate says, what the data is showing. If it's within performance specs, it doesn't need to be adjusted. If it's out of performance specs, then an adjustment needs to be made. And that's where people kind of run into trouble here. In critical HVAC sensors, they're calibrated using different methods and different associated accuracies for those methods. Really pays to ask, what am I getting? What did you do to my instrument? How did you do it? Where is it? The terminology used here simply reflects that very few sensor designs perform perfectly linear. There's very few designs. Most often, a calibration laboratory will use, as you see there, a nonlinear quadratic curve to fit the performances needed. So don't be afraid of the data. It's showing what's supposed to be there. That 0.999, that's a pretty good fit. Anything above 0.90 is good. This is an almost perfect fit for the data. So I would have good faith in this sensor that it's working properly, especially for a critical HVAC application. But along with that sensor came back some kind of certificate. So I would take a look and see what's in that certificate. Hey, am I getting? Is this just a certificate of conformance telling me a lot of blah blah blah? Kind of that's mostly a trust me kind of document. And it may only refer to the company's quality control. You need to look for a reference to a national reference laboratory or a standard, such as NIST, NIST for the USA, DIN in Germany, JIC in Japan. Those kinds of terminology is what you need to see on the certificate. Here's your SRM, standard reference material that was used. It conforms to NIST, and there's calibration data here. So the certificate of calibration, it may or may not include adjustment data, but at a minimum, it must show as found and as left data. Meaning, any adjustments, the as left data as it left the laboratory that were made to the instrument upon receipt, which are the as found measurements, those adjustments were required to bring it into published operating specs, published by the manufacturer. So it is important to be able to look and see, do I have as found and as left data for my instrument if there was an adjustment made. If there was no adjustment made, you'll have as found and as left data, and they'll be within spec. You'll see immediately that they're within spec. So important to know the difference between the two certificates. And if you're getting charged for this, ask for your money back. There are industry-accepted report formats on data collection, and really the reason here we get on this part of the message in critical HVAC is it's all about the data. There's industry-adopted reports, especially in test and balance applications. There's a lot of situations where the pencil and paper method is still used, and that's fine. My question is it defendable? Can you defend that? Can you defend the data that's there using pencil and paper? A lot of critical HVAC techs will use user-designed templates, meaning they built their own. Are they flexible enough? Is there enough security in user-designed templates to do the job? If you buy a third-party template, you go out and you buy a package on the outside. Are they adaptable to the application? Can changes and adjustments be made in that template, or are you stuck with what you bought and don't have the ability to report things the way they need to be reported? At a minimum, there must be date, time, parameter, instrument used, serial number or numbers, and the readings, reading or readings that are used. If you don't have that, you're shooting in the wind to be able to justify a critical HVAC job. And there are many software packages specific for an instrument. If that goes with the instrument and that's all you have to work, what happens when the instrument's down? Or worse, found to be out of calibration. And I guess that holds true to any report format. Now what do you do? with all the jobs that went before, for all the hundreds and hundreds of measurements that were made in a critical HVAC application. Now what do I do? Some of the data security, not only data collection, data reporting, but there's also data security issues in critical HVAC. I'm assuming standard computer security protocols are there. Many times, critical HVAC data is set up with 3 levels of users. There's a user, the person, the tech, whoever it happens to be, entering the data. There's a power user, a manager, department group, whatever, that has the capability of getting down deeper into the data and not making changes or adjustments, but managing the data input-output. And then there's an administrator at the top, and there should only be one that has overall view of that. There are certain data entry protocols. There's a certain way to put data in that needs to be followed in critical HVAC. Critical HVAC data, there should be just one-way data entry. No corrections or alterations can be tolerated. And a growing question right now, a lot of subscription packages are based in the cloud. So my question then is, not only mine, but a lot of people are asking, okay, so who owns the data up in the cloud? Is it mine? Is it yours? Is it both of ours? I don't know the answer to that. That needs to be researched, and that needs to be defined up front before you choose a package. And there's proprietary information as well. Many critical HVAC applications, the data that's generated, it's confidential. It's proprietary. Building owners or managers don't want to be sharing that kind of information around. Which one of the mechanical contractors has access to that data? Which of the subcontractors can have access to that data? If there's a certifying agency coming in that needs to certify that job, how do they get access to that data? And how do you ensure that it doesn't get passed around? Will it be stored online or offline? And any past data, any historical data, if something has routine, reoccurring certification or validation, there's a lot of past history. How is that handled? How does that come up? Third-party subscription type software. I mean, who owns that data in the cloud? It's not a casual question. It has an awful lot of bearing and an important import now when the government has to sit down and spend money to break into somebody's iPhone. Who owns that data? Can we control it? Can we make sure we know where it goes? And I think just as importantly, making sure it can't be altered. I mean, today we're all enamored with the digital side of our business, with the digital side of instrumentation. It's so easy to go in and adjust and correct and modify. In critical HVAC, that's just not tolerated or shouldn't be tolerated, especially for an application like this. For example, the pharma industry. There's a federal law. That's 21 CFR, Code of Federal Regulations. It originally was written to permit a wide use of electronic technology. Well, the problem is allowing people to have free access, allowing anybody in critical HVAC to have free access to the data to go in and modify it anytime they need is just not acceptable. So there's a problem of how do you regulate access to the data? What's more important, the instrument or the data that it's generating? And you know, the hackability, I guess to call, of the measurement instrument and their associated data files. Should this continue to be a concern? You've got to be able to take your measurements. You've got to be able to do the job efficiently, affordably, and correctly. But having a restrictive electronic measurement protocol and technique doesn't help you. So that's pretty much a quick run through, a quick view, glance down down the road of critical HVAC. I'd like to open it up for any questions. Any?
Yeah, hey Bob, we did have a handful of questions come through and hopefully you can address.
Good.
Initially, well, one was just sometimes we fly through acronyms. Sometimes somebody was questioning one of the acronyms, the SMACNA, which is what was the sheet metals.
Oh, SMACNA, yeah, it's a sheet. It's the sheet metal union. It's a sheet metal association. It's a union of sheet metal workers that will they will go and bid on a job, and it's just like a musician's local or whoever. But they're qualified, certified professionals who do a great job. I guess they can do residential, but 90% of what they do is commercial duct installation.
Okay. And then if you could, I kind of got into it a little bit, but just a little more clarification as far as the that are critical and non-critical applications.
I'm sorry, Thomas, it's tough to hear you.
Oh, I'm sorry. Can you hear me now?
Now I can, yes, sir.
Okay. Again, we're discussing the difference between critical and non-critical environments, and just a little better clarification on what might fall under each.
Okay. A warehouse might not be a critical environment, although many warehouses today they might be temperature controlled, but there's really no need to worry about any of the parameters we talked about, other than maybe temperature if there's liquid stored in there. A critical environment, there might be a pharmaceutical warehouse, and that might really be much more restrictive in temperature. There may be worries about material freezing. A lot of pharmaceuticals need to be stored within a very tight temperature range. If there's powders being stored there, there might be a very tight relative humidity window that it must be held within. If there's any off-gassing of any of the pharmaceutical packaging or whatever, it might need a much higher air changes per hour within there. So there's a warehouse, and then there might be a pharmaceutical warehouse that requires a higher level of control, a higher level of not only measurement but of control as well, for example.
Okay. And then we were discussing a little bit of the instruments and the accuracy and the kind of certifications you should be looking for.
I'm sorry, Tom. Can you repeat, please?
Can you hear me now?
Yes, sir.
All right, let's try this again. There was questions about different sorts of instruments, and I guess there can be some variation in pricing, accuracy, and such. How what can you look for that the difference that you're paying for an instrument that is going to be give you the accuracy you need? I guess specifically, what should you be looking for?
That's really pretty straightforward in my mind. It's not just a question of price, although I agree. Normally you get what you pay for. Published accuracy, higher levels of published accuracy, an instrument that's let's say published at plus or minus 1% accuracy versus something that's published, say, plus or minus 10% accuracy. I would normally expect to pay a little more for that 1% accuracy instrument, but along with the accuracy should come additional design advantages and benefits built into that instrument. Easier to operate, easier to enter data into, most important, easier to get data out. It's probably going to have data logging capabilities so that and normally would come along with, let's say, a software disk, a CD, so that you can load an app or a data collection package onto your laptop or PC, interface that instrument to that software package, and preload a day's worth of work onto that, so that you've got both your data and your data collection format on the instrument and on your PC, so they both back one another up. It makes data collection, makes data handling and supervision a lot easier. Third, for me, would be an instrument design for critical HVAC really should come with a NIST certificate. There's no excuse, there's no reason why something that important, those measurements, that important, would not come with a NIST certificate. And it should be included in the price of the instrument and not as an option.
All right, fantastic. Yeah, we're kind of at the hour mark here. I want to try to wrap it up. So, Bob, we really appreciate you helping us out here. A lot of good information here. Again, we do have this recorded. We will make this webinar available at our website at raco.com under our trainings page. Same with the slides. We'll make the slide deck available there. So give us a few days and we'll get that up there. And we'll have a follow-up email to everyone that's attended or signed up, so you can pass this along and, like I said, share with your friends. So again, thanks for being with us. Our next webinar is going to likely be at the end of May. We're still organizing that, but keep a lookout for an invite, and hopefully you can join us for that as well. So thanks so much, and we'll talk to you all soon.
Super. Thank you so much, Tom. Thank you all.